Okay. Hello everyone. Very good evening. I welcome you all at India's most comprehensive preparation platform for all competitive exams, that is BYJU'S Exam Prep. So guys, in this session, we are going to discuss some most important questions of the topic instruction pipeline. So guys, there are two topics in COA which are most important. One is instruction pipeline. Another is memory organization. Almost every year, a question is asked from these two topics, right? So 4 mark questions are guaranteed from this two particular topic. You can be sure for that, right? So let's begin the session with instruction pipeline. So this is brief introduction of myself. My name is Vishal Rabatia. I have 10 plus years of teaching experience. Following are the achievements and areas of expertise. Apart from that, this is my Telegram group. If you guys have any doubt related to GATE preparation, whether it is CS branch or DA paper, you guys can connect me for your problem. Apart from that, there's an announcement. BYJU'S Exam Prep is going to conduct a national scholarship test for all GATE aspirants on 29th of October between 9 a.m. to 9 p.m. Do participate in this test. If you perform good, then you may avail up to 90% off on all our programs. And tonight at 7:30 p.m. simultaneously, Richa Gupta ma'am is conducting a workshop for GATE 2025 and GATE 2026 aspirants, basically for GATE 2025 aspirants, that how they can or what strategies they can utilize to ace the GATE 2025 exam, right? Now, apart from that, BYJU'S Exam Prep has launched the mega mock test. The next test for computer science branch will be on 28th of October. That is at Saturday 12 p.m. This test will be for programming and data structure, algorithms, and operating system subjects. So this is a full-length test that will consist of 65 questions. Time duration will be of 3 hours and it will be a 100-mark paper, right? So participate for whether you want to attend the scholarship test or workshop, or you want to appear for the mega mock test. You just need to download the application of BYJU'S Exam Prep and need to register yourself using your mobile number. Now, the link for the BYJU'S Exam Prep app is available in the description. You can download it from there and simply register yourself using your mobile number, and you will be able to get all the benefits. Okay. Good evening, Manish. Good evening. And apart from that, the crash course is going on for GATE 2024 aspirants. So if you are looking for the options that from where you can eventually brush up all your knowledge, then this is the course for you. You can simply enroll for that particular course. This is the contact number which you can use for the purpose of connecting the team. At the same time, the GATE 2025 and GATE 2026 courses are also live. You can enroll them using the same contact number. Okay, so guys, let's start with the very first question of the instruction pipeline. There's a tricky question. Generally, the time, by what value the time is increasing, that information is given in the question, but in this particular question, they are simply increasing the speed, right? So we know that the speed and time are proportional, but in what sense? If we increase the speed, then the time will reduce, right? So here they are trying to increase the speed, therefore the time will reduce. If the speed increases, then the time required for the execution of program will decrease. But is there any linear dependence between speed and time? That's what we need to see in this question. So in an enhancement of our design of our CPU, so you already have a design. Now you are trying to enhance that particular design. The speed of floating point unit has been increased by 20%. So the circuit in the CPU which are performing the floating point operation, the speed of that particular circuit has been increased by 20%, and the speed of the circuit which is performing fixed point operation has been increased by 10%. Okay, now it is being asked that if we do so, then what will be the overall speed up achieved? What is the overall speed up achieved if the ratio of the number of floating point operation to the number of fixed point operations are 2:3? Means if we take 5 operations, then 2 out of them will be floating point operations and 3 out of them will be fixed point operations. If this is the scenario, then what will be the overall speed up? Clear? Am I audible and visible? Just 1 minute. Yeah, right? So that's it. Please try to understand. And the floating point operation used to take, if you are performing the floating point operation, then they are used to take twice the time taken by the fixed point operations in the original design. In the original design, so let's try to understand. So we are simply looking for the speed up. We are simply looking for the speed up. So how do I define the speed up? Sir, speed up, because time is inversely proportional, therefore speed up will be time taken by old design. Yes, sir. Divide by time taken by new design. That's the speed up which you are looking for, right? But how do you understand this particular thing? So, sir, there's a design in which there are two different types of units. One is for fixed point and one is for floating point. Now, let's try to understand that in the original design, if the time required by the fixed point unit to perform the operation is t, let's assume t, don't call it t1, t2, etc. Simply keep it t. So if it is t, then in the floating point unit, it is already given that the time required will be twice. So the floating point operation used to take the twice the time taken by the fixed point operation. So if the fixed point operation are being performed and if they are taking t amount of time, then floating point operation will take 2t amount of time. Yes or no? Now my question is, in the new design, what will be the time? In the new design, what will be the time? So please try to understand. If speed is 1, then the time will be t. If the speed is 1, whatever, 1 unit something, then the speed will be, then the time taken for floating point unit will be 2t. Now, what is being given, that the floating point unit, the speed of the floating point unit is increased by 20% and the speed of the fixed point unit is increased by 10%. Then what will be the reduction in the time? What will be the reduction in the time? So the time for new device for the fixed point operation will become t upon 1.1 because the speed has been increased by 10%. Similarly, this will be 1 upon 1.1. 1 upon 1.1, it will not be 10%. That's the idea. That's what you need to understand, that because this increment is not in the time, or this decrement of 10% is not in the time, it is in the speed. So we all know that speed and time will be inversely proportional. So if we decrement or if we increase the speed by 10%, then the time is guaranteed to decrease. But will it decrease by 10%? No, sir. Inversely proportional. So 1 upon 10%, right? Similarly, for floating point operation, the time will be 2t. Earlier it was 2t, now it will become 1.2. Clear? Okay, sir. So this will be the overall time, because 20% increase in the speed is 20% for floating point operation, increase in the speed is 10% for the fixed point operation. So now in this case, what will be the time taken? So let's assume that overall 5 operations are performed. So in the 5 operations, overall if 5 operations are performed, then 2 will be fixed point operations and 3 will be floating point, because it is given that the ratio of the number of floating point divided by fixed point is 2:3, right? So let's assume 5. So it will be what, sir? For 2, time taken by old design will be what, sir? For 2 operations, each one of them will take t unit of time. So 2 is 2, 3, to understand that why this 2 is coming. Now for 3 operation, the time taken will be 2t. Yes or no? The time taken will be 2t. Because 3 operations are floating point operations, the time taken by them will be t unit of time. 3 operations will be floating point operations. For the time taken by them will be 2t, right? Similarly, the same operations, 2 operations of floating point unit, if they are executed on the new design, then it will be 2 divided by t upon 1.1 plus 3 into 2t. The time will be 2t upon 1.2. Time will be 2t upon 1.2. So let's try to solve this using a calculator. This number will be a little clumsy. 1.81. This thing is nothing but 1.81, 818, and this thing will be 6 upon 1.2. This will be 5. So numerator, it will be 6 plus 8 divided by 6. Did I did something? Let's look at this. So two floating point operations, two floating point operations. Oh, ratio to the number of floating point. Just 1 minute. Floating point are 2 and fixed point are 3. Sorry. Floating point are 2, so it will take 2t amount of time. Fixed point are 3, so they will take only 3t. So 2, so just 1 minute. So the ratio is 2:3 for floating. I thought fixed divided by floating. I read it as fixed divided by floating, but it is floating divided by fixed. So 2 will be for floating. For floating, it will be 2t divided by 1.2. And for fixed, it will be t divided by 1.1. Yes, sir. So this will be the time. So numerator will become 3 and 4, 7. This denominator will also change. Don't worry. See, the only thing is that 2 are the floating and 3 are the fixed. So for 2 floating point operations, the time will be 2t. For 3 fixed point operation, the time will be t. Right? So it will be 7t. So t got cancelled out. That's fine. So 4 divided by 1.2. 4 divided by 1.2 will be 3.33 plus 3 divided by 1.1. 2.72 plus 3.33, 6.05. Yeah, so this value will come out as 1.157. This value will come out as 1.157. Clear? Okay, sorry. Let's start this. So this is the idea. The time taken by old design will be nothing, but if there are 2 floating point operations, then what will be the time taken by them? Plus, if there are 3 fixed point operations, what will be the time taken by them? That's simple. Divide by, if there are 2 floating point operations in the new design, then the time taken will be 2t divided by 1.2. And again, if there are 3 fixed point operations, then the time taken by them will be t upon 1.1. And the result will come out as, the speed up vector will come out as 1.157. The speed up vector will come out as 1.157. So the correct answer will be option A. Clear? Any doubt with this? I hope this is clear. Let's move to the next question. So please, what is important here? What is important? Sir, if we are simply saying that the decrease or increase in time is of 10%, then we can simply use 1.1t or 2.2t. But here the increase is not in time, but the increase is given in the speed. Therefore, you need to make sure that there is not linear dependence between speed and time. It will be 1 upon 1.1 and 1 upon 1.2. It will not be exactly 10% decrement in the speed for floating point operation. It will not be the decrement of the, it will not be the decrement of 10% in the time taken by floating point operation. It will not be the decrement of 20% by the time taken by floating point operation. So that's the logic. So please make sure that what information is given, you use that you use the correct information. Next question. So please try to understand. The instruction pipeline of our RIC processor has the following stages. Okay, instruction fetch stage, decode stage, operand fetch stage, perform operation stage, and write back stage. Done. Now, fetch, decode, operand fetch, and write back stage are taking 1 clock cycle for every instruction. Whatever the instruction is, 1 clock cycle is required by this particular stages. Consider a sequence of 100 instructions. Right. Now, the perform operation stage, in perform operation stage, 40 out of those 100 instruction takes 3 clock cycles, 35 out of those 100 instruction takes 2 clock cycles, and 25 instructions are taking 1 clock cycle. There is no problem. Right. Now, assume that there are no data hazards and no control hazards. So, no data hazard or control hazard, but there is a structural hazard. Yes or no? What type of structural hazard? That while one perform operation unit is being utilized by one instruction, the next instruction will not be able to use it. So if there are structural hazards, then obviously stall cycles will be present until that particular stage or that particular unit or function unit becomes available. Clear? Now, the number of clock cycles required for the completion of the execution of sequence of instruction. How many stall cycles will be required? How many clock cycles will be required? Please try to understand. Please. Sir, when we discuss the performance evaluation of performance evaluation of pipeline processor with stalls, what do we say? Sir, if there are n instructions which are executed over a k stage pipeline, then at least k plus n minus 1 cycles will be required. K plus n minus 1 cycles without stalls. Right? But, so this is without stalls, how many cycles will be required? But we just need to calculate in this particular question that how many stall cycles will be observed. How many stall cycles will be observed? Please try to understand a simple concept that if every stage takes 1 clock cycle, if every stage takes exactly 1 clock cycle and there is no data dependency, no control dependency or no hazards, then ultimately each instruction can be executed in 1 clock cycle. That means average CPI will be almost equals to 1, and in that case no stalls will be observed, right? But in this particular case, the stage perform operation stage is taking more than 1 clock cycle for certain number of instructions, right? So for 40 instructions, the cycles taken by the perform operation stage are 3. So anyway, 1 clock cycle is required. You cannot avoid that. But those 2 clock cycles will be extra. So for 40 instructions, 2 clock cycles will be stalls. So for 40 instructions, how many stalls? 2 stalls. Right? Similarly, for this 35 instructions, they are taking 2 clock cycles. So one is fine, one is required, but next that another 1 cycle is stalled for this 35 instructions. So for this 35 instructions, 1 stall. Right? And for 25 instructions, because they are taking only 1 clock cycle, therefore no stall will be associated with them, therefore 0 stalls. Right? So if I ask for total stalls, these are 80 stalls because of the 40 operations which are taking 3 clock cycles. There will be 35 stalls because of the instructions or operations which are taking 2 clock cycles, and 0 stalls. So ultimately 8, 3, 11. So 115 stall cycles are observed during the execution of those 100 instructions. Now, sir, these are the number of cycles without stalls plus those many stall cycles will be observed. So what will be the value? So K value is, this is a 5-stage pipeline. This is a 5-stage pipeline plus n value 100 instructions are being executed minus 1. These are without stalls plus 115 stalls are observed. 115 stalls are observed. This will be 104 and this, so 219. Correct. So who answered 219? Satish, 219 cycles. Yes. So obviously 104 cycles will be without any stall cycle, but 115 stalls will be observed when we are executing those 100 instructions, in which 40 are taking 3 stalls, 40 are taking 3 clock cycles, and 35 are taking 2 clock cycles. That's also simple. Let's move to the next question. This will define how average CPI can be calculated in presence of stalls. So consider, so these are the different types of questions which can be asked from the topic of pipeline in the GATE exam. So consider a non-pipeline processor operating at 2.5 gigahertz frequency. So okay, the current frequency is of 2.5 gigahertz. It takes 5 cycles to complete an instruction. Oh ho 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 ho. A non-pipeline processor. Sir, if this is the clock frequency, then what is the what will be the cycle time? So T equals to 1 upon F. T equals to 1 upon F. So I can write it as 1 upon 2.5. This is gigahertz. So 1 upon 2.5 nanosecond simply, right? So 1 upon 2.5 will be what? So this will be 0.4 nanosecond. Right, sir? So cycle time for non-pipeline processor is of 4.4 nanosecond. Cycle time for the non-pipeline processor is of 0.4 nanosecond, and it is being said that for the execution of one instruction, it is taking 5 clock cycles. That means, so instruction execution time, let's look at this. Execution time using non-pipeline will be what? Execution time using non-pipeline will be number of cycles into cycle time. That's a simple concept. So number of cycles taken are 4. The cycle time is 0.4 nanosecond. Therefore, each instruction will require 2 nanosecond. Each instruction will require 2 nanosecond. That's one option. Now, you are going to make a 5-stage pipeline out of this processor. So, whatever this processor is, we are trying to divide the operation of the CPU into 5 different stages. But you all understand that some of these cycles, some of these stages may take more amount of time, some of these stages may take less amount of time. So, based on the division, it is observed that you will have to decrease the frequency. That means the cycle time will increase. So, you are going to make a 5-stage pipeline out of this processor. Overhead associated with pipeline. So when you are trying to divide it into pipeline, some of these stages are taking more amount of time, and you need to complete the operation of that particular stage also within the given time. Therefore, the time period of the cycle or the cycle time will increase. That means the frequency of the processor will decrease. Right? So force you to operate the pipeline processor at a 2 gigahertz processor frequency. So if the frequency becomes 2 gigahertz, then the cycle time will become 0.5 nanosecond. The cycle time will become 0.5 nanosecond. Now, in a given program, assume, okay, in a given program, so let's try to understand. If this is your program, then what is given? So 30% are of what? 30% are memory instruction, 60% ALU instruction, and rest are branch instruction. Okay, so 30% are memory instructions, 60% are ALU instruction, 90 gone, 10% are definitely branch instruction. So that is what is available. What else do we know? Sir, okay, look at this. 5% of the memory instructions. So not all. So this is already in the percent. So let's assume if we talk about one instruction, if we talk about one instruction, then what is the probability that it will be a memory instruction? Sir, the probability is 0.3. So with the rate 0.3, it will be a memory instruction. And apart from that, with the rate 5%, that means with probability 0.05. With probability 0.05, this is the memory instruction which will cause stalls in the pipeline. So 5% of the memory instruction cause stalls. If they are causing stalls, there will be 50 clock cycles. The stall will be of 50 clock cycles, means because of one stall cycle created because of memory instruction, the number of stalls will be 50. If one instruction is creating stalls, then there will be 50 stalls in the pipeline. See, this is very obvious. The reason is given that each due to cache miss. So if you are not able to find the data in the cache, then ultimately you will have to access the main memory, and main memory is a slow device with respect to CPU. Therefore, memory operation time will be very low. Therefore, a significant amount of time will be wasted. Right? So it's okay. So if we are talking about one instruction, then with rate 0.3, it will be memory instruction, and with probability 0.5, it will observe 50 stall cycles. Okay, sir. So that's one thing. Sir, with what rate it will be ALU instruction? Sir, with rate 0.6, it will be an ALU instruction. With rate 0.1, it will be a branch instruction. So let's try to observe this, right? Now, and 50% of the branch instruction causes stalls of 2 cycles each. So it's also given that when it is a branch instruction, 50% means 0.5. 50% of the branch instruction will cause stall cycles. Each one of them will cause 2 stalls. Each one of them will cause 2 stalls. Okay, sir. Apart from that, assume that there are no stalls associated with the execution of ALU instruction. So with rate 0.6, this instruction will be an ALU instruction and no stall will be associated with this, therefore 0. Right? So with respect to one instruction, on an average, how many stalls will be observed? On an average, how many stalls will be observed with respect to one instruction? That's what we need to understand, right? So these are the stalls which will observe with respect to one instruction. Let's calculate them. So this is something which will take time. So 0.05 into 50 into 0.3, so 0.75. This will be 1 into 0.1. Overall, it will be 0.85. So per instruction, the number of stalls will be 1.85. Let's try to understand what is the significance of this. One instruction. If we think of one instruction with rate 0.3, it will be a memory instruction. With rate 0.6, it will be a ALU instruction. With rate 0.1, it will be a branch instruction. And in the corresponding situation, the number of stalls are also given. So if we think of one instruction, how many stalls will be observed? So because of one instruction, on an average, 0.85 stalls will be observed. Now, what is being asked in the question? For this program, the speed up achieved by the pipeline processor over the non-pipeline processor will be what? So, it's simple. So, how do we define the concept of speed up? So, speed up will be average instruction execution time using non-pipeline. Average instruction execution time using non-pipeline divided by average execution time using pipeline. That's what we define. Yes, sir. It's very simple. So average instruction execution time for the non-pipeline processor is already known. So it will be nothing but number of cycles into cycle time. So same concept will be in the denominator also, that number of cycles divided by cycle time, but this time the number of cycles will be something else. Number of cycles into cycle time. So with respect to non-pipeline processor, 5 cycles are required, each of 0.4 nanosecond. So with respect to pipeline processor, how do we define the number of cycles? Average CPI in pipeline is what? Sir, average CPI in pipeline is defined as what? I don't know whether you understand it or not, but please try to understand. Average CPI in pipeline will be 1, because ideally this should be 1, that if there are no stalls, then the average CPI will be 1 plus number of stalls per instruction. So with respect to one instruction, how many stalls are observed? I hope you have seen this formula, 1 plus number of stalls per instruction, which comes in the denominator when you are calculating the speed up calculation. So 5 plus 0.4, now this will become 1 should be this value, plus number of 1 is the average ideal CPI plus 0.85 into cycle time for the pipeline processor is what? Sir, cycle time for the pipeline processor is 0.5. Cycle time for the pipeline processor is 0.5. So let me calculate this also and you will get your answer. Sir, this will be 2 divided by 0.5 divided by 1.85. So this will be 2.16. This will be 2.16. So they are asking up to 2 decimal. Therefore, the correct answer will be 2.16. So this value will be 2.16. Is it okay for everybody? Clear? So the correct answer for question number 3 will be 2.16 is the speed up. Clear? Sir, what was important here, that how do you calculate the average CPI in presence of stalls? How do you calculate average CPI? So all the questions are different. All the questions are different. So in this particular case, for a certain number of instructions, if a situation is given, how many stalls will be observed? This first question is related to enhancement in the design of the CPU. Second and third are related with the number of stalls. Let's look at the type of fourth question. So the fourth question is related to the concept of operand forwarding. So consider a pipeline processor with 5 stages. Okay, instruction fetch, instruction decode, execute, memory access, and write back. Each stage of the pipeline except the execute stage takes 1 clock cycle. Okay, so it will again create problem, because if one particular stage cannot complete its operation in 1 clock cycle, then it will eventually create stalls in the pipeline. Assume that the instruction decode stage, okay, merely decodes the instruction, okay, and the register read is performed in the execute stage. So generally what do we assume? Generally we assume that the decoding stage itself will perform the operation, operand fetch operation. But in this question, it is given explicitly that decoding stage will merely decode the instruction. In the execute stage, you will fetch the operand and you will also perform the execution. So both of them will be performed in the execution stage only. The execute stage takes 1 cycle for add instruction, okay, and 2 cycles for multiple instruction. This is what is given, that except execute stage, all other stages can perform their operation in 1 clock cycle, but execute stage will take 1 clock cycle for addition and 2 clock cycles for multiplication. So there will be some stalls because of this multiplication. Ignore pipeline register latencies. Okay, so buffer delay need not be included. Consider the following sequence of 8 instructions. So add, multiply, add, multiply, add, multiply, add, multiply. Okay, assume that every multiplication instruction is data dependent. So this multiplication instruction is data dependent on the add instruction just before it. So add, this multiplication is dependent on this. 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 And every add instruction except the pass, obviously, because before pass instruction there is no other instruction, therefore we cannot define the dependency of pass instruction on any other thing. So this add instruction is data dependent on the multiplication instruction just before it. So this addition will be data dependent on this multiplication. This addition will be data dependent on this multiplication. This addition will be data dependent on this multiplication, etc. So that's what we know. So this is the actual scenario. Now what is given? The speed up is defined as follows. So the speed up is being defined as that what will be the time required for the execution of this 8 instruction without operand forwarding, and what will be the time required for this 8 instruction if we use the concept of operand forwarding. This is what we are defining. The speed up achieved in the executing the given instruction sequence will be what? So that is what is being asked. So let me define it. That sir, there are. So this question is actually time taking. I do understand that you will realize, sir, too much time will be required. Yes, but if 2 marks will be there for this particular question, but if you are struggling with time, then my suggestion will be to analyze that yes, this particular question will require the construction of the space-time diagram for the execution of this instruction. So you can be little choosy that you may try to attempt this type of questions. In the end, when you know that I will definitely be able to solve this type of questions, but let me first check whether sufficient time is available or not, right? Because of this particular question, you may leave 2 or 3 questions because the time is required. So, sir, what will happen, sir? Add is the pass instruction, then multiply, then add, then multiply, then add, then multiply, then add, then multiply, right? So this is the idea. So what are the stages? So fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, write back. Yes, sir. It's simple. So what will happen? So instruction fetch, instruction decode. Sir, it is addition, therefore it will require only 1 clock cycle. Execute, memory, write back. Sir, multiplication. Now what will happen, sir? It will be fetched here. It will be fetched here. First, we are thinking in terms of without operand forwarding. So you will not be able to get the data until the write back operation writes the result into the register. Therefore, you can decode it here. You can decode it here because in the decoding stage you are not fetching the operand, but in the execute stage you will try to fetch the operand. Therefore, execution can be performed here only. Now, after execution, this is a multiplication. Therefore, execution stage will require 2 clock cycles. After execution, you will perform the memory operation. Then you will perform the write back operation. Then what, sir? This instruction can be fetched here. Because the decoding stage already in the instruction, therefore decoding will be performed here. Next execution will be performed here. Then after that you will perform the memory access. Then you will perform the write back operation. Right, sir. For multiplication, you can fetch when it is being decoded, and you can decode it here. Then you will try to perform the execution. This execution will eventually require 2 clock cycles. So after execution, memory access and write back. Clear? So again, addition, when you are fetching the past, when you are decoding the previous instruction, you can start fetching it. When you are starting execution, you can start decoding it. Then when operation is, the result is available, then you will perform the execution. With respect to addition, it will require only 1 clock cycle, then memory, then write back. So some symmetry is there. You will eventually realize that if I tell you that how many cycles are already elapsed, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Now, please try to understand. The next one will be, next instruction will be what? So, next one will be multiplication. So, multiplication will require 4 more after this write back of the previous instruction. So 19 plus 4, this multiplication will end at 23. So this addition, after this it will require only 3. So 23 plus 3 will be 26. Now after 26, this multiplication will require 4 more, that is 30. Clear? So how many cycles will be required? How many cycles? So you can construct it completely. You can construct it completely by following the same method. But if you are observing this, then you will know that okay, this is done. After the write back of the addition, the multiplication will require 4 more cycles. After the write back of the multiplication, the addition will require 3 more cycles. After the write back of addition, the multiplication will require 4 more cycles. After the write back of multiplication, the addition will require 3 more cycles, and so on. So this multiplication will require 4 more, that is 19 plus 4, 23. Addition will require 3 more, 23 plus 3, 26. Multiplication will require 4 more, 36, 26 plus 4 will be 30. So 30 with execute, without operand forwarding. So, sir, we are trying to calculate the execution time without operand forwarding will be 30 cycles will be required without operand forwarding. Now, let's think that how many cycles will be required with operand forwarding. With operand forwarding. So, sir, with operand forwarding, what will happen? The things will change. Things will change. You don't have to wait until the write back operation completes. As soon as the output of the previous instruction is available at the execution stage, you can take it from there only. Right? So please try to understand this. So what will happen? Look at this. So instruction fetch, decode. Now it is trying to perform the execute. Sir, yes, it will be able to perform the execute because it requires the output of the previous stage which is available. But the execution stage itself will require 2 clock cycles. Therefore, execute, then memory access, then write back. Sir, what will happen with respect to addition? It will be fetched, it will be decoded. But can we start executing the addition instruction, this addition instruction in the 5th clock cycle? No, sir, because at the end of 5th clock cycle only the multiplication operation will produce its result. Therefore, at the beginning of 6th clock cycle, you will be able to fetch the operand. So execute, memory, write back. Again, sir, after this execute, you will require the multiplication will require execute. Then after this to execute, addition will require only 1 clock cycle, execute. After this, the multiplication will require 2 clock cycle, execute. Then after this execution, the addition will require only 1 clock cycle, execute. After this execution, multiplication will require 2 clock cycle, execute. And finally, there will be memory and write back. So, sir, how many clock cycles? 1, 2, 3, 4, 5, 6. Let me write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Sir, overall. So it may look like, it may not be in exact accordance with this timeline. Let me rewrite them if you are getting confused because of this cycles. So, sir, this will be fifth one, yes, 6th, 7th, 8th, 9th, 10th, 11th, this will be 12th, 13, 14, 15, and right back will be with respect to 16. So please try to understand that 16 clock cycles will be required when you are using the concept of operand forwarding. So in this case, the number of cycles with operand forwarding will be 16. So 30 by 16 will be what? So 1.875. So the answer for this question will be 1.875. Okay. Done, sir. Let's move to the next question. This is the question number 5. This is related to the division of an stage into, already you have a pipeline, but you are trying to divide the existing stage of the existing pipeline into 2 or more stages. So some type of this type of question may also be asked. So an instruction pipeline has 5 stages. Okay. So there are 5 stages. What are they? Sir, instruction fetch, instruction decode, or that's okay. Next one is execute. Next one is memory access, and next one is write back. So these are the 5 stages. Now the time is also given. So the time is also given. What? So with the stage latency is 1, 2.2. So this is 1, this is 2.2, this is 2, this is 1, this 0.75. Right. So which one is taking maximum amount of time? So this decoding stage is taking maximum amount of time. So they may think that the cycle time will eventually depend on this particular thing. The cycle time will eventually depend on these 2 stages which are taking maximum amount of time. Then they may choose to divide them further, right? So what is happening? So to gain in terms of frequency, because this time if the cycle time is more, then the frequency will be low. If you reduce the cycle time, you will be able to increase the frequency. So to gain in terms of frequency, the designer have decided to split this particular stage. This decoding stage is being split into 2 parts. Sir, what are they? Sir, into 3 stages. Okay, this stage is being decoded, is being split into 3 stages. One will perform the instruction decoding, another will perform the register fetch for first operand, another will perform the register fetch for second operand. Similarly, each of latency, equal latency, so 2.2 is getting divided equally into this 3 operation. 2.2 divided by 3, 2.2 divided by 3, 2.2 divided by 3. Remaining will remain same. Also, the execute stage is split into 2 stages. Okay. Now, they thought that, okay, we have reduced 1, but still, if we have divided decoding stage into 3 stages, then still the cycle time will depend on the execute stage. So let's divide this also into 2 parts, that is execute 1 and execute 2. This time each of latency will be of 1 nanosecond. So yes, sir. Now the new design has a total of 8 pipeline stages. Yes, sir. 1, 2, 3, 4, 5, 6, 7, 8. Right. Now what is being asked is the total of 8 pipeline stages. Now a program has 20% branch instruction. Okay. In our program we have 20% branch instruction which execute in the execute stage and produce the next instruction pointer at the end of execute stage. So it is being said that generally if a branch instruction is there, then it will produce the outcome at the end of execute stage, right, in the old design, and at the end of execute 2 stage in the new design. So do you realize that what will happen whenever the branch instructions are executed? Because of branch instruction, some unwanted instruction some unwanted instruction will be present in the pipeline and you need to flush them out of pipeline. Clear? So that's the logic. So when the execute stage, in this particular case, execute stage is the 3rd stage. Therefore, the number of stalls that will be present in the pipeline, because in the old design will be only 2, because the branch penalty is 3 minus 1, that is 2. But in this new design, 1, 2, 3, 4, 5, 6, the execute 2 stage is the 6th stage. It is the sixth stage in the new pipeline. It is the third stage in the old pipeline. So if it is the third stage, then the branch penalty will be of only 2 cycles. In this particular case, it is the sixth stage. Therefore, the branch penalty will be of 5 cycles. Do you realize that concept? Next what? Now, all instruction other than branch instruction have an average CPI of 1. Means no other problem in the pipeline apart from the execution of branch instruction. What is being said? The execution now. Yes, all instruction other than branch instruction have an average CPI. Was okay. The execution time of this program on the old and new design are P and Q nanoseconds respectively. So the program which is having 20% branch instruction, for that particular program, the execution time on the old design is P and the execution time on the new design is Q. Now it is asking that what will be the value of P by Q. What will be the value of P by Q? So please try to understand P by Q will be execution. P is the execution time on the new design, old design. Execution time on old design divided by execution time on new design. Sir, please try to understand. The concept is very simple. What, sir? Execution time will be number of instruction. They will be same. Number of instruction in the old design and the new design will be same. Nothing changes. So this 2 will get cancelled out, right? In this particular case, you just need to identify the average CPI into cycle time. In this case also, you need to identify the average CPI into cycle time. Yes, sir. Now, please try to understand. Average CPI in the old design will be what? Sir, generally, there will be average CPI of 1 plus this 20% instruction, that is with rate 0.2. With rate 0.2, some stalls will be observed. How many? Because the execute stage is the third stage, then because of one branch instruction, 2 stall cycles will be observed. So, this is the average CPI. This is the average CPI for old design into the cycle time for the old design will be obviously 2.2 because maximum among this 5 is 2.2. Maximum among this 5 is 2.2. Right, sir? Now, so what will be the average CPI for new design, sir? Obviously, all of them are taking 1, but 20% are still the branch instruction, and because the target address is available at the 6th stage, therefore, branch penalty will be of 5 clock cycles into, sir, sorry, this is 2.2, not 2.5. This 2.2. Right? Here also, this will be nothing but, sir, what will be the cycle time? Sir, 2.2 will be what? This is 7.5. So, 2.2 divided by 3 will be 7. So, which one will be less? 0.75 or 2.2 divided by 3? Yes, sir. 2.2 divided by 3 will be less. So, this will be the cycle time. 2.2 divided by 3. So, can I do this? That this 3 will eventually become numerator. So, sir, this will be nothing but 1.4 into 3 divided by 2. That's something is in front of me. 1.4 into 3 divided by 2. Does it come out as 2.1? Do we have an option for this? No, sir. So, please, I hope these calculations are correct. 1, 2, 1, 2, 4, 1.4 into 3. So, this is, for me, it is coming out as 2.1. Please cross check. For me, it is coming out as 2.1. So, the value of P by Q will be 2.1. Clear? Value of P by Q will be 2.1. Is this clear for everybody? Yeah, love with code. I don't know why this is the reason, but yeah, I'm observing it for a quite long time that the low attendance is there in these sessions. Fine. So please try to understand execution time of old design, new design, number of instructions will be same, average CPI into cycle time, average CPI into cycle time. Average CPI will be what, sir? Ideally it should be 1. How many stalls, sir? With rate 0.2, the two stall cycles will be observed, therefore 0.2 into 2. Now in the new design with rate 0.2, same, because the number of number of branch instructions are not changing, but there will be this execute stage will be the 6th stage, therefore the penalty will be of 5 clock cycles, therefore this will be 0.2 into 5, that is average CPI will become 2. In the original case average CPI will be 1.4 only, but in the original case the cycle time was 2.2, in the new case the cycle time becomes 2.2 divided by 3. So for me this 2.1 should be correct. Okay sir, last question, that is the 6th question. I asked you to discuss 6 different types of questions in the instruction pipeline. So a 5-stage pipelined CPU has the following sequence of stages: instruction fetch, read, execute, memory access, write back. Right? So don't worry, this definition read, instruction decode and register read. So generally we know it as instruction decode. It is nothing new, right? Now data memory access, that's okay. So again, this explicit definitions may confuse you, but this is the exact same stage. It is saying data memory access for write access. If you are performing the write operation, the register write at the read stage is used. Obviously, that's what we do, right? Register write back. Consider the following sequence of instruction I1, I2, I3. We want to execute them. Let each stage takes 1 clock cycle. So what is happening? Load. So content of location. So this location. Content of location, not 101. Content of location 1 is stored in the register R0. Then R0 is added with R0 and result is stored in the R0. Then content of R2 is subtracted. From R2, the value of R0 is subtracted and result is stored in R2. That's fine. Now, what is being said? What is the number of clock cycles taken to complete the above sequence of instructions starting from the fetch of I1? Starting from the fetch of I1, that how many cycles will be required? So please try to understand. That's this is your clock cycle 1. We'll fetch the first instruction. We will decode in the first instruction. There will not be any problem. Let me call it RD. Then in the third stage is execute. So what will happen, sir? Nothing will happen, but ultimately 1 cycle will be required. Then memory access, write back. Memory access, write back. So obviously this 5 cycles will be consumed for the very first instruction itself, that is what's a load R0 location 1. The next instruction will be add R0 comma R0. Now my question is, sir, the value of R0 will be available in the, so the value of R0 is the value which is being accessed from the memory and being loaded into the register R0. So until we perform the write back operation, we will not be able to decode it. So though we will be able to fetch this instruction into the second cycle itself, but in the read stage itself we need to fetch the operand. What has happened, sir? In the read stage, instruction decode and register will be read, but you can read the register value only when it is available in the register file. We are not using the concept of operand forwarding. By default, if nothing is given in the question, then you do not use the concept of operand forwarding, right? So R0 will not be available until the end of the write back stage. So the decoding can be completed here only. After this decoding, you will perform the execution, then you will perform the memory access, then you will perform the write back. So sir, 6th, 7th, 8th and 9th clock cycle. Now what will happen? So the last one is subtraction of R2 comma R0. Now the result will be available in the write back stage. The new result also needs to be written into the register R0. So though you may be able to fetch it here, so you will fetch it here, but the read can be performed only in the 10th stage. Then you will perform the execution, then you will perform the memory access, then you will perform the write back. So do you realize 10, 11, 12, 13 cycles will be required? Yes or no? Do you realize that if we do not use the concept of operand forwarding, what is the number of clock cycles taken to complete the above sequence of instruction, right? So if we start from instruction fetch, read, execute, memory access, write back, there is no other dependency. I hope you understand that every stage, each stage takes exactly 1 clock cycle. But the idea is you are writing into the register until the value of R0, until the value of location is available in the R0, it cannot be used. Until the value of R0 is available, it cannot be used. So there is data dependency. There is data dependency. If nothing is specified, then we will try to solve this problem without operand forwarding. But when we are using the concept of without operand forwarding, how many cycles are needed? Sir, 5, 4, 9 and 4, 13 cycles are needed if we are not using operand forwarding concept. Clear? If we are not using operand forwarding concept. But in this particular sequence, the option 13 is not available. What does it mean? Perhaps this question is with respect to, that is the understanding. If the 13 is available, then we will definitely mark the correct answer as 13, because by default we do not use operand forwarding, right? But in this case 13 is not available. So what will we do? Sir, we will try to utilize the concept of operand forwarding. We will try to utilize the concept of operand forwarding. No sir. Now what will happen? Sir, we will be able to decode the instruction in this particular stage itself, because the content of memory location 1 will be available after the memory access stage. Therefore, we'll perform the read, then we'll perform the execute, then we'll perform the memory access, then we'll perform the write back. So for this next instruction, R2 minus R0, this is R2 minus R0. So we'll fetch this instruction here. Then though we are not able to perform this read operation, but we can perform this read after this execute, because the value of R0 has been evaluated by this execute unit, which can be accessed by the operand forwarding, and the R2 is directly available in the register file. So after that you will perform the execute, then you will perform memory access, then you will perform write back. So 10 cycles will be needed if we use the concept of operand forwarding. Right? Without operand forwarding, 13 cycles will be needed. With operand forwarding, 10 clock cycles will be needed. 13 is not available. Therefore, the correct answer for this question will be 10. That is with operand forwarding. So these are the different questions which we have discussed from the concept of instruction pipeline. Tomorrow, we will discuss 6 more questions. We'll discuss 6 more questions from the topic of memory organization. This is another most important topic of computer organization and architecture. Clear? So this is it for this particular video. If you like the video, then please hit the like button. If you are new to the channel, then subscribe for the channel and press the bell icon to get the notification about our upcoming videos. That will be all for this video. Thank you very much. Keep learning. Good night. Take care.